Hey, um, thank you so much, Diane. Kalina Ferrado of the Integral Group. Kalina is a principal and a mechanical engineer at the Integral Group leading their San Diego office. She has over a decade of sustainable engineering experience in Canada and the United States across a broad range of building sectors, including commercial, higher education, Alice, if you're out there, hospitality, life science, and healthcare. Kalina takes a holistic approach to design, striving to create healthy, enjoyable, and environmentally responsible spaces, while minimizing the size and complexity of the mechanical systems. Working in collaboration with the design team, she focuses on building trust and maintaining an open dialogue with her teams, both within the Integral Group and with the wider project team. Kalina is a recipient of the Consulting Specifying Engineer Magazine's 40 Under 40 Award in 2015, and Plumbing and Mechanical Engineer Magazine's Mechanical Engineer of the Year Award in 2018. She is a registered professional engineer, a LEED accredited professional, and a well accredited professional. Welcome, Kalina. Woo!
Thank you. I'm just going to share my screen here. I tried it a second ago and it pulled up the wrong screen. So let me see if I can get the right one.
That's it.
All right, yeah, but I need you guys to see the full version.
But now it's being presented as like an image on the,
oh, sorry.
It's okay.
Try this one more time. Are you seeing the full screen presentation, or are you seeing the quick overview?
Yeah, we're seeing the preview version where you can see the next slide. Don't worry, this is literally the second time this exact same like PowerPoint presentation.
Yeah, I might give up on it and just go to the PDF version in a second, but it's fine.
That's what redundancy is for in design.
Yeah, and that's maybe just what we'll go ahead and do.
And just so everyone knows, the topic, we're talking about best practices of zero carbon large commercial construction as part of the overall theme of trying to cover all the different building types. Presentation that follows is industrial decarbonization. That's going to be fascinating. How do we do this with all the different things we're doing in society? Okay, take it away, Kalina.
Okay, I finally got it. Sorry for the technical difficulties there. Thank you very much. Again, I'm Colleen Ferreira. I'm an engineer and principal at Integral Group. For those of you that don't know of Integral Group, we are a deep green engineering firm. So we do MEP as our core engineering, but we take a very holistic approach to that. So we have planners and building modelers and policy experts, all sort of working under the same umbrella to really inform the work that we do. And when we look at what we do, we talk about sort of our vision or our values that inspire us. And so that's trust, nurture, inspire. When we look internally, and so we're all a very motivated group of passionate people. But these four on the left, imagine, perform, accelerate, sustain, is how we try to think about what we do out in the world. And so this is, kind of identifying what these issues are is that imagine. And right now it's the climate emergency that we're in. Perform is figuring out how to do it and doing it, and then really accelerate and sustain is what we're doing here today. So we can't solve this climate emergency if it's just me and the people in my office doing this. So what we want to do is make sure that we're sharing the knowledge, we're getting best practices out there, and really transforming the industry sort of collectively and collaboratively. So that's what I'm here to do today. I really do want to make sure we're sharing resources. I have a lot that I want to try to cover in a short period of time. And so I have shared this presentation with the folks at Redwood. I'm happy to share it with you. I've got some links built into it so that if you want to look at anything in more detail, you can. But just as kind of a heads up that I will be covering a few different things and referring to a few different documents. Really starting with this one. And so we have developed with our UK office and actually a task force of about 100 different volunteer professionals, developed a climate emergency design guide. And that's really focusing on the emergency of climate change and carbon, and trying to design for zero carbon. And so we have a presentation if you want to see that focused on this, or you can download those guides directly for free. And they really take sort of a step-by-step approach to what we need to focus on and how we need to get there for zero carbon design, looking at sort of the overall embodied, the operational carbon, but also doing a deep dive into the embodied carbon. And when we're talking about zero carbon design, we really need to make sure we're looking at that. So whole life cycle carbon, looking at the operational carbon, which is shown there in yellow. And the conversation about operational carbon is often very similar to the conversation about net zero energy. It's not quite the same, and I want to talk about some of the key differences today. But then also making sure that we're looking at embodied carbon that goes into it first for the initial construction of the building, and then your replacement and maintenance elements throughout the life cycle, and then the end of life cycle. So it's a much more holistic look than just the ZNE conversation, but there is certainly a lot of overlap between the two of those. Now, one of the things that Climate Emergency Design Guide, I think, does quite impressively is take what is really a complex issue and distill it down to this, they call it their one-pager for zero carbon design. And it focuses on these 5 key areas, or at least identifies 5 key areas to really consider when you're taking a zero carbon approach to buildings. So the low energy focus, that's energy efficiency. That's where a lot of the conversation is pretty similar to ZNE, and really driving your efficiency and optimizing your building to reduce the energy usage. Measurement and verification being identified as like a fundamental core item. So we've got to make sure that if we're going to design these buildings, that when we start them, they operate correctly. But then looking at it over the long term to make sure that you maintain that operation, right? So we need to design these buildings to operate at zero carbon on day one, but also make sure we're maintaining that over the whole lifespan of that building. Embodied carbon was what we had talked about before, as far as just the amount of carbon it takes to maintain or manufacture all of those items. The climate doesn't care if that carbon came from your boiler or if it came from a mining site. We need to be looking at carbon sort of at both ends. So that's sort of the building side carbon use, and then you start looking at the energy sources. So the building energy sources, it sounds like I don't need to convince this crowd to get fossil fuels out of buildings. So certainly leaning towards the building electrification as a necessary first step. But looking not only at sort of how that electricity is generated on site, how the profile of how it's used over the course of the day becomes really important in the carbon conversation, more so than I think it gets addressed in the ZNE conversation. And so how the building interacts with the grid and maintaining that zero carbon balance and actually hitting it and achieving it over time. So there's a lot to digest in this, and I think I only have about 20 minutes left to cover it. So I'm really going to focus on some key elements of the energy use and that integration with the grid, and really focus on sort of some of the new elements that are different from the conversations we've been having in the past about ZNE, because I think all of those conversations are really important, but when we make the leap from zero net energy to zero carbon, there are some ways that we need to think differently. And the first really important item to drive home is the way we are setting targets and goals. And this is a change. When we first started designing for high performance buildings, we've been looking at relative energy metrics. So we're always designing to be 10% or 20% or 50% better than an equivalent baseline building. And what we need to do is shift that line of thinking to stop thinking relative and start thinking in absolute metrics. So actual energy use intensity per square foot per year. And that's going to be different for different building archetypes, but it needs to be a fixed number. And that's really important for 2 reasons. The first is just the way it drives design. So one of the issues that we've always run into with a relative metric is that some of the really core elements of good design, so the building footprint, the orientation, the glazing percentage, in a relative baseline approach, you can design a great big tall glass skyscraper, and as long as your glass is sort of 10% better than the baseline, it's still going to show up as a high performance building or an efficient building in the model. And in reality, what we need to be doing is is hitting fixed targets so that we do optimize the building envelope and we start optimizing the footprint and really getting benefit from that in the way we evaluate our metrics. So the first reason it's important to look at an absolute metric is the way it drives design and design decisions. The second is looking at it from a more, is if we want to be able to scale zero carbon designs and be able to address it at scale and grid level and city level and really transform our built environment, we need to start thinking of it as an energy budget. So not an aspirational goal, but if we look at our grid and we look at how much electricity we have available for our buildings and start dividing that by the built environment, then we can come up with a budget of electricity we have available per square foot. And stop treating that as a goal and start just thinking of it as a firm budget that we now have to work within and use that to drive our design. And that way we can start thinking about these buildings, because that's the only way we're going to be able to do zero carbon in cities and at scale, because cities, we can't just do zero carbon buildings as those one-off sort of greenscape sites where we've got great big flat roofs that we can put our PV on. In order to take our city zero carbon, we do have to think of it at a grid level. So we need to think about how our buildings are interacting with the grid and be able to have that grid provide the energy for these buildings, because they won't be able to do it themselves. There's just not enough roof area to support this kind of density. So we need to shift our thinking, and we need to think of our buildings as part of the grid that they interact with, not as standalone elements that then, and thinking of the grid as this infinite sink, because it's really not. And we need to be starting to integrate those more directly. And it needs to be adaptable, because this grid is going to be changing hopefully pretty rapidly in the next years and decades, right? So right now it's a mix of a lot of these fossil fuel burning energy sources. And we've got renewables increasingly coming on, and it sounds like that conversation has been had in a few other sessions before me, as far as just the rate of renewables coming on. So we know our grid is going to be changing, but right now we have this very mixed grid. So not all energy is the same from a carbon standpoint. And throughout the day, how much energy or how much carbon is associated with that energy is going to vary throughout the day. So this is one of those key areas where the zero carbon conversation is different from the zero net energy conversation. In that in zero net energy, we treat, a kilowatt hour of electricity the same no matter what. And it's really not when we start looking at the carbon. So the time of use of that energy becomes really important. And one of the ways to think about that is if we think about what our grid produces for electricity, it's going to be a mix of renewables, and we've still got some of those fossil fuels on there. But the base load fossil fuel plants, to meet that base load emission, those power plants are fine-tuned to their best efficiency point. So we're still producing emissions, but these ones are the ones that are humming along, dialed in at how they can produce that with the fewest emissions possible. As soon as we need to start changing that to meet fluctuating demand, that's essentially what happens when you first start a car, or if you watch a car accelerate up the highway and you see these big bursts of smoke coming out the back. When you have a combustion process and it needs to deal with adapting and change and starting and revving up, that's where you start getting a lot more emissions. So if we have to take our grid and adjust it to these big swinging peaks and differences in demands, the difference that we get in emissions is considerably more. And so there's a talk about marginal emissions, that not every kilowatt hour is linearly related to the amount of carbon that comes out of that. So to reduce carbon emissions, it's not just a matter of reducing the amount of energy you use, it's leveling off the way you use it. And so to demonstrate an example of that, this is a project that we were doing at Swarthmore College in Pennsylvania. They contacted us because they are not only going to increase their campus square footage, they're adding about 50% more building area. They also have carbon goals that they want to meet. So what we did is we looked at their campus. The dark orange line is their current energy load profile. We said, okay, you're going to build all of these extra buildings. So that essentially doubles it. So you can see the gray line there. If you look at their summer months where they're cooling, it essentially takes that energy load and just bumps it up, right? So that's just more square footage. If we then also take these buildings and get them off their gas, so we shift it to electricity, this is in Pennsylvania. So you shift to gas heating in the winter, you can see that electricity loads in the winter skyrocket, right? Because that was gas that we used to be burning that we don't want to burn anymore. in order to bring this down, step one was that energy efficiency, so use less. So we went through a bunch of building energy retrofit options with them. But then step two was, okay, how do we level off those peaks? And so by putting in the battery storage, what that orange line shows is a storage and solar plan that lets them level off those peaks. So we're still using more electricity than they are right now because they're adding that square footage and they're getting rid of their gas. But by leveling off those peaks, we can keep the carbon emissions associated with that electricity much lower. And that prepares them to be buffered for variations in the grid so that they can maintain their consumption at the lowest emission point. So this is where thinking about when you use your electricity and maintaining that at an even rate, rather than treating the grid as a gigantic sink-in source, is a mindset shift that we need to make when we're shifting from a Z&E conversation to a zero carbon conversation. Oh, sorry. So we go into, if you want to hear more about that or go into some of those studies in more detail, again, this is a reference I'm happy to share with you. We have another presentation on that that goes into it in a bit more detail. But essentially, it sounds like I don't need to convince this crowd about building electrification. Certainly listening to the presentation that I just heard before, getting fossil fuels out of our building and off of our grid is going to be a necessary step. To do that, we need to optimize the efficiency in our buildings first through a lot of the really sustainable, like high performance design approaches we've been taking getting to this point. The difference that we need to make now to get to zero carbon with that building electrification is shifting to heat recovery and heat pumps, getting away from just really efficient boilers, and starting to think about grid integration. We don't want to think about our buildings as standalone islands, but really thinking about how they interact with that grid and being able to level off those peaks. So incorporating demand response and energy storage into our designs, building in a demand response system that can monitor that grid so that you know how carbon intense your energy is at any point in time, so that when you're drawing a kilowatt hour of energy in the morning versus in the afternoon, your building can respond to that and can shift that so that it's at the lowest emission point. And when the grid is peaking, when they are having to bring on those peaker plants, having your building and your site be able to respond to that. Now that can be through load shedding. So that's resetting your thermostats up, shutting down unnecessary plug loads, turning down some lighting. So you can change the operations to shed that load, or you can have the on-site storage to be able to produce that or meet that load from your site instead of the grid. So that can be electrical storage and batteries. It can also be thermal storage to offset the loads from your HVAC system, both on the heating and the cooling side. So I want to go through a couple of case studies. Again, for the sake of time, I'm not going to get in, I won't necessarily have time to get into them in a lot of detail, but I think just highlighting some of the key elements that we did incorporate, and I want just a couple of lessons learned that we went through with them. So the first one is the J. Craig Venter Institute. This one's down in San Diego in my backyard. This was the first ZNC designed lab in the world. So it is all electric. We designed it about 10 years ago now. I think it opened in 2013. And so this one does incorporate thermal storage. So we have big water tanks built in the parking garage. So when we're cooling the building all day, we dump the heat into the tanks. And then in the evening when we need heat, we pull that heat back out and we use it to heat the building. It also incorporates its own PV array. One of the big lessons learned from here, and this sort of speaks a little bit to that absolute metric versus a relative metric in the modeling, is that the other thing that gets lost in a relative modeling approach is the plug loads. Because the plug loads get assumed to be the same in both your model building and your base load building. There's not the same level of scrutiny that gets applied to them. And so for this particular project, the plug loads that we thought we were designing around ended up being quite different from the actual operational loads after the fact. What I think we found was that a lot of the old freezers and equipment that they were using in their previous labs got moved over, so it wasn't as efficient as we were expecting. And there was just a lot more of it. This is a genomics lab, so they have lots of cryo freezers. And so those plug loads were something that weren't accurately represented, and it didn't show up because it was a relative model, right? With absolute modeling, you have to be really, really careful about really dialing in the actual plug load performance. And that's actually a comment that, you know, is certainly important in a lab, but even in office spaces, as spaces are becoming really efficient on the building side, plug loads are now starting to represent, you know, upwards of 40% of your building consumption. And so really engaging with the users to understand how they're going to use their space, how many computers they're going to have in there, what other process equipment they're going to have in there, and getting them to engage with how that operates, being able to shut that down so that they don't have unnecessary loads. That ends up being sort of one of the longest processes when we're actually starting up a building to get it to operate as designed, is really the user training. The next project I want to kind of highlight and talk about a little bit is the Exploratorium. So this was again a ZNE zero carbon design we did in San Francisco. This one we really did look at the embodied carbon aspect of it. So the existing structure and envelope of this was maintained as much as it could be. Now, partially that was because of historic reasons. So there was a lot of historic drivers in here. The historic nature of needing to preserve the interior elements also prevented us from being able to upgrade a lot of the installation. So we had a lot of specific challenges on this. We overcame those with some of our mechanical systems. So we did radiant systems instead of trying to cool the entire or heat the entire airspace. We also actually integrated the seawater for our heating and cooling mechanical systems. So it was, I mean, in this case, we put in some pretty clever mechanical systems to be able to offset some of the limitations we had with the envelope. But this one, we were able to really kind of deep dive into the embodied carbon side and make sure that that side was getting accounted for, not just the operational carbon, which is where a lot of the focus traditionally is. The last one I wanted to look at with you here, just to talk about some key elements, is the Kaiser Santa Rosa medical office building. So when we did this one, I think it was the first medical office building to be ZNE verified. And this one here, whereas in the previous cases, like I said, we put in, you know, heat recovery and energy storage, we had some really clever mechanical systems. This one, we actually took the different approach. This one, we said, okay, let's design this building and zone it out so that we can use really simple systems used in a clever way. So we put, it's just pretty straightforward packaged DX units on the roof, but we zoned it so that each exposed element portion has its own system. So if you're familiar with the way mechanical zoning often works, is that you just put big chunks of the building on the same system, and then you kind of heat and cool and reheat as needed to make sure that you get the right amount of heating or cooling where you want it. By grouping the elements together so that they all see the same load, each of those systems may operate at a different temperature at any given time, but they're never needing to reheat because we've zoned it so that they all see the same load at the same time. So by doing that, by going all electric, we saved them their gas service. So we didn't bring any gas utility to the site. The way we zoned it, we got rid of all the reheat requirements. So we got rid of all the hydronic piping from the project. We were able to save them $1 million in first costs and still deliver a verified zero carbon project. So this one I think is really important because a lot of the conversation about ZNE or zero carbon design, it gets a lot of pushback from the cost side. And that's just really not the case. So done right, or understanding those priorities or what they want to achieve at the outset, it can actually be far more cost effective because we can save a lot of those utilities by not having to spend the extra energy to distribute it. So that, again, I was touching sort of pretty high level on a few just key elements. These are two, again, freely available resources from PG&E. They do a deep dive into both the J. Craig Venter project I talked about and also the Exploratorium. That Kaiser project we did after these were published, so it's not in there, but I'm happy to share more information if anybody wants to know more about that one. I've only got a few minutes left, so really just to kind of wrap up the key points that when we're looking at this and how zero carbon needs to be thought of differently from the way we've been approaching zero net energy. Really the focus on fixing an absolute EUI budget and treating it like a budget. It's not an aspirational goal. We need to start thinking about this as a fundamental driver and design criteria that we have to meet. Building electrification, getting our fossil fuels out of our buildings, and being able to integrate with that grid. We really need to be paying attention to the grid and the time of use of our energy, not just a net metering of in and out, and being able to adapt to a changing grid. So it does need to be responsive, because we know our grid is going to change. So the time of use equation that we have now is going to change over time as that grid becomes more renewable, and we need our buildings to be able to adapt to that if we're really going to design resilient infrastructure for the future. So that's zero carbon where we're at now. Like I said, we're always kind of looking at what the next challenges are and how we're going to address those. So grid stability and integration, we talked about needing demand response at the building level. That needs to happen at the grid level as well, and those need to be able to interact and respond to each other. So really thinking bigger about how our buildings tie into our grid, and how we can respond to that. Battery and energy storage technology really needs to develop. So we really need batteries to balance out those peaks. But from an embodied carbon standpoint, batteries have their own challenges. So a lot of our batteries are based on rare earth metals. They have a lot of embodied carbon in them themselves. And so looking at evolving technologies, a lot of our battery technology comes from smartphones, and looking at super high energy density and lightweight technology. For stationary building batteries, we don't need that. So we can look at other lower carbon options and different technology. But making sure that we are looking at things from a life cycle and embodied carbon standpoint. So I think there's more awareness around embodied carbon of the building elements, but we're starting to do more research about embodied carbon of the MEP system specifically, and also looking at refrigerants. So I think as we get off gas, we're going towards heat pump systems, which means we're putting a lot more refrigerants in buildings. Again, refrigerants themselves bring their own challenges from global warming potential. And so I think that's going to be another kind of next future that we have to look into and how we're going to solve. We are currently looking into this in our office. We are doing research if you're interested in knowing more. Again, we've got another presentation you can look at for that. But I think I'm out of time, so we've got just a couple of minutes here. If we have time for a question or two, I'm happy to take them. If not, you're welcome to email me or contact me separately.
Woo! Yay! Taking on the big buildings, gorgeous ones too. Thank you so much, Kalina. There are a couple of questions over there. I had one for you that was related also to Chuck's, which is, have you had a chance to work with PV glass? You know, like these commercial buildings, some of them have just that facade of the city that you showed, like just all glass buildings. Have you any thoughts on PV glass?
So I have not myself. We've worked with a few different kind of glass types. So I haven't worked with PV glass. The challenge with, I mean, you're talking PV integrated glass, so we're generating from the glass surface,
Yep.
right?
Yeah.
I mean, the challenge is that you get your best efficiency from having, you know, more things closer to horizontal than to vertical. And a lot of the glazing ends up being shaded by adjacent elements. So, you know, I think where so I haven't seen it incorporated in a lot of my projects. We have worked with chromatic glass, and like different glass that will respond to change, you know, so it'll change to a darker opacity, depending on the solar load. So we've incorporated some glass technologies that way, but I haven't worked with the PV itself.
Well, thank you again.